Good morning, YouTube. Here's a quick summary of what we did today. We're talking about related rates problems. Here's 88 AB4, the free response question number 4 on the 88 AB exam, 1982 AB4. A ladder 15 feet long is leaning against the building so that that the end X is on level ground. The end Y is on the wall, as shown in the figure. X is moved away from the building at a constant rate of 1/2 foot per second. Find the rate in feet per second at which the length OY is changing at the instant that X is 9 feet from the building. So everything's moving, right? OX is changing, OY is changing. YX is not. That's the length of the ladder. Then everything's moving, and you take a snapshot the moment that we're 9 feet from the base of the building. X is 9 feet from there. And at that moment, how fast is Y changing, right? Okay, so here's what we did. We modeled it with a little right triangle. Wish we did it this way, actually. Okay, so here is the building, here is the ground, and here is the ladder. Alrighty. And we just said instead of OX, we just call this X. Here's a right triangle. Instead of OY, we just call this Y. Instead of YX, we just call this Z. And the thing is that they gave you dxdt. dxdt, how fast this is moving, was 1/2 foot per second. Now, if we're pulling that away from the base of the building, the ladder is sliding down, so dy dt is going to be negative, and that's what we're looking for. The length y is decreasing. dz dt is 0 because it's a ladder, it's not changing the length. So to get the related rate, relating dy dt to dx dt, first you have to have a relationship between x and y, and clearly it's Pythagorean. All right, so if we differentiate implicitly with respect to time, it's sort of like the chain rule. Stuff squared gives you 2 stuff, derivative of the stuff with respect to t. In this case, x prime is correct if you want to write x prime instead of dx dt, plus 2y to the 1, power rule, dy dt. Stuff squared gives you 2 stuff to the 1 times the derivative of the stuff, chain rule. Equals, now z is a constant, so you get 0. Or 2z dz dt and dz dt is 0. Now you can cancel out the 2's if you want. Divide everybody by 2. You could write it this way if you like. And plug in what you know. Let's see. X at this instant is 9 feet. X prime was 1/2 foot per second. Y, we don't know. But we know that z is 15 and we know that x is 9. Isn't that a 3, 4, 5 right triangle? 3 times 3 is x is 9. 3 times 4 is y is 12. And 3 times 5 is 15 is z, 15 feet. So y is 12 feet. If you have to plug in x into the first equation, x squared is 9 squared and z squared is 15 squared. You can solve for y. 12 feet here. And we're finding y prime or dy dt if you like. Right? So you got 9/2 plus 12y prime is 0. So 12y prime, trying to get y prime alone, is negative 9/2. So divide by 12, and y prime is negative 9/24. But if you want to reduce by, what, 3? Negative 3/8 feet per second, right? Because the dy dt, y is in feet and t is in seconds. Maybe you want to leave it dy dt, you know? So every second, if nothing else changes at this moment at least, the height, the y is changing 3/8 of a foot, decreasing that much. Okay, part B says find the rate of change in square feet per minute, per second, of the area of the triangle OXY, or XOY, whatever, at the same instant that x is 9 feet. So anything that you got from A, you can use in B. Namely, if you need dy dt is negative 3/8 feet per second, you can use that. Plus all the other givens are valid for at this instant that x equals 9 feet. So let's do it. Well, clearly, what's the area of a triangle? 1/2 base times height. So 1/2 times x times y. All right, so the area is 1/2 xy. And you can do the power rule, product rule here, as you differentiate implicitly with respect to t. You could keep the 1/2 outside and just differentiate xy times the half. Or keep the 1/2 as one of the products, times y as the other. All right, so a prime or d dt is going to be the first times the derivative of the second, plus the second times the derivative of the first. There you go. And let's plug in what we know. We're trying to find dAdt. And so what do you get? Well, x was 9, so you got 1/2 times 9 times dy dt we just got is negative 3/8, plus the y we figured out was 12 times the half, times the x dt was 1/2 foot per second, positive. All right, just work this out. Let's see, negative 27/16 plus 3. Well, 3 over 1 is how many sixteenths? It's 48/16. So you're going to get 21/16, and it's the dAdt, so square feet per second. All right, so at this moment, if nothing else changes from now on, we're increasing 21 square feet every 16 seconds. How about that? Or every second, we're increasing 21/16 of a square foot in area. Okay, good. All right, how about 85AB5? Was another one we did. Here it is. Okay, the balloon shown above is in the shape of a cylinder with hemispherical ends of the same radius as that of the cylinder. The balloon is being inflated at a rate of 261 pi cubic centimeters per minute. That's your dVdt. At the instant that the radius of the cylinder is 3 centimeters, so r is 3 centimeters. At this instant, when we take a picture while everything's moving, then we just take a snapshot, and that moment, that's what it looks like. The volume of the balloon is 144 pi cubic centimeters, and the radius of the cylinder is increasing at a rate of 2 centimeters per minute. What's in parentheses did not show up on the BC exam. The volume of the cylinder is pi r squared h, and the sphere of the volume of a sphere is 4/3 pi r cubed. At this instant, what is the height of the cylinder? Now, just like in the previous example, we had to figure out y. They didn't give us y before we could do the rest of the problem. Here they're giving you a hint. You better figure out h before you do the rest of the problem. So, part A is not calculus. It's just some algebra, really. And then we'll get to the calculus, the related rate stuff in part B. So, what is the volume of this balloon? Well, it's the volume of a cylinder in between, right in the middle, is pi r squared h, plus 2 hemispheres of the same radius. So isn't that just one big sphere? So here's your volume. The volume of the cylinder plus the volume of the 2 hemispheres, which is one sphere. Right? Now let's plug in what they gave us. They gave us that V is 144 pi cubic centimeters. R at this instant is going to be 3. H is what we're trying to figure out. Plus 4/3 of pi times, and then R again is 3. So let's work this out. We've got 144 pi here equals 9 pi h here. And one of the 3's cancels, so 3 squared is 9 times 4 is 36 pi. So subtract the 36 pi from the 144 pi, you get 108 pi, or you can cancel out all the pi's first if you like, is 9 pi h, and 9 pi into 108 pi is 12 centimeters. So we've got that at this moment, the height of the cylinder is 12 centimeters, and the radius is 3 for both hemispheres and the cylinder. Okay, so part B now. At that instant, how fast is the height of the cylinder increasing? So, let's take the same relationship for V and differentiate it implicitly with respect to T. And let's see what we get. Okay, so V, let's see, V is 4/3 pi r cubed for the 2 hemispheres plus pi r squared h for the cylindrical part. So dVdt is going to be 4/3 pi 3r squared dr dt. Because we're differentiating r cubed with respect to t, so it's stuff cubed. Chain rule. Plus, how about we do it this way? First times the derivative of the second, plus a second times the derivative of the first. Whoops. Let's see, 2 pi r dr dt. All right, so plug in what we know. They gave us that dVdt was 261 pi cubic centimeters per minute. And that r is 3. And these 3's cancel, by the way. Might as well get rid of these 3's. There you go. So it's 4 pi 3 squared. They gave us the RDT is 2 centimeters per minute. R is 3 centimeters, okay. Plus pi times 3 squared again. DHT is what you're trying to figure out. So solve that algebraically, like that's x. Plus, okay, h is 12 times 2 pi times r is 3 times the RDT is 2. All right, let's simplify all this mess. Wow, look at this. Okay, 261 pi equals, okay, 3 squared is 9, times 2 is 18, times 4 is 72 pi. Okay, plus 9 pi dHdt. You could cancel out all the pi's, I guess. Plus, is that 144 pi, I think? 2 times 2 is 4, times 3 is 12, times 12 is 144 pi. All right, so how about we combine the 72 and the 144 is 216. Let's subtract that from both sides, and you get 45 pi is equal to 9 pi dHdt, divides both sides by 9 pi, and dHdt turns out to be 5 centimeters per minute. There you go, perfect. Alrighty. All right, let's try another one. One more. Where did it go? This one. A circle is inscribed in a square. This is 9485. As shown in the figure above, we'll just draw our own. The circumference of the circle is increasing at a constant rate of 6 inches per second. All right, so dCdt is 6 inches per second. All right. As the circle expands, the square expands to maintain the condition of tangency. By the way, what's in parentheses is not given on the BC exam. C is 2 pi r, and A is pi r squared for a circle. Find the rate at which the perimeter of the square is increasing. Indicate units of measure. All right, let's do that. So let's draw this stuff. Here's a circle. And here's a square. No, what happened there? What happened to my square? I'm going to hit square. Not quite. Oh boy. Not happening. Why is this not cooperating? Oh, not bad. Let's say that's good. All right, so let's say that this is the radius of the circle. So the side of the square is 2r. They want you to find the rate of change of the perimeter. What's the perimeter of the square? Isn't that 8r? All right, so P equals 8r. Alrighty. And so what's dPdt? That's what they want, the rate of change of the perimeter. That would be 8 dRdt. What's our dRdt? Well, the circumference is given, right? So dCdt is going to be 2 pi dRdt. But they gave you dCdt was 6. So divide by 2 pi and you get 3 over pi. Whatever the units are. What are the units? What are the units? 6 inches per second. Okay. So the units are in inches per second for dRdt. R is in inches. T is in seconds. So plug that in over here, and you get 8 times that, and you get 24 over pi inches per second. If this is non-calculator section, leave it like that. You want to get a decimal equivalent on a calculator section, be my guest. Okay? And one last question. B, at that instant, at the same instant that the area of the circle is 25, well, at the instant that the area of the circle is 25 pi square inches, find the rate of increase in the area enclosed between the circle and the square. So the area between the circle and the square, isn't that the area of the square? minus the area of the circle, right? So the area of the square, would that be the side 2r all squared, 4r squared, minus pi r squared? Okay, let's do that. So the area that we're talking about, that shaded area, was the area of the square, which is 2r all squared, like this, minus pi r squared, the area of the circle inscribed. Okay. So I want the rate of change of that area, right? So d A dt is going to be, well, let's see, what is it going to be? It's going to be 8r dr dt minus 2 pi r dr dt. All right. And they said at the instant, where am I? At the instant that the area of the circle is 25 pi r square units, right? So if that's pi r squared, r is 5. Okay. And presumably the RDT is the same throughout. They didn't say that, but I'm going to assume that. All right, so r is 5. The RDT is 3 over pi. They should have said that the rate of change of r is not changed between part A and part B, whatever. Minus 2 pi times 5 times the same thing. And we'll clean this up a little bit. Let's see, 120 over pi minus, here the pi's cancel, and you get 30. Whatever that is, that quantity. Now that's the ADT, so that's square inches per second. That's it. Very good. All right, YouTube, that was a quick summary of what we did today. We didn't record because we were working in groups and stuff, so it was hard to record all this concisely. And there you have it. No calculator today. Sorry, didn't need it. Bye-bye.